All right, guys, Stat 1150. The purpose of this video is to start trying to teach you something called the normal model. And there's probably nothing that I hear students, even at the graduate level, mess up any more than the normal distribution. Once they learn about the normal distribution, turns out they want to make everything a normal distribution, and it turns out that's just completely inappropriate. What happens for the most part is once we begin the normal distribution, we're starting to examine the relationship between samples and populations. Now remember, a sample is a subset of a larger population. So population tends to be the entire group of subjects, elements, dogs, cats, trees, whatever it is under investigation. And typically there are so many subjects or elements or dogs or cats or trees in our population that we can't examine, collect measurements on all. So what we do is we take a sample and we use this sample to make an inference about everyone in our population. Now we do this all the time when we elect a president. But before the, well, we don't do it when we elect a president, but we do it before when we're trying to determine how people are going to vote and predict a winner. So the population would be all people who are going to vote. Well, you can't get all that information because there's too many. But what happens is these polling agencies go out and take a sample and they use these measurements to make an estimate of how the entire population is going to vote. Now, what happens relative to normal distributions in samples and populations is the following. When we have a sample, we can reasonably, with a graphing calculator or StatCrunch or Minitab or SPSS, we could create a histogram. And we may, if we got a histogram that looked like this, we may describe it as being a bell-shaped and symmetric distribution. And you'll even see a lot of technology and even a lot of people that will draw this nice continuous smooth curve to illustrate the general shape of the histogram. It turns out in populations that we also, and guys, this is a huge if we were able to go into the population and take the measurements on every single subject, element, dog, cats, trees, whatever it may be, and create a histogram, there are certain types of histograms that would form a perfect bell-shaped and symmetric distribution. Perfect. Now over here I do this intentionally that this bar was higher than this bar so we don't have symmetry. But we do kind of have a bell-shaped and symmetric distribution. This is kind of a bell-shaped and symmetric distribution. It's not perfectly bell-shaped, it's not perfectly symmetric, but it's close enough where we can say, well, it's kind of bell-shaped and symmetric. But guys, oftentimes in populations, we have these distributions that are perfectly bell-shaped and symmetric distributions. And when we have these, we call these things a normal distribution. Now I said earlier that there's probably nothing where my students screw up more than normal distributions. And here's what happens. Students will go out and collect a sample. They'll put their sample in Excel, they'll import it into R or StatCrunch or some statistical software package. They'll shoot out a histogram and they'll say, oh look, I have a normal distribution. No, you don't. Normal distributions do not come from samples. Normal distributions are theoretical. They represent an entire population. And in fact, you can't even go out and collect this data. There's this distribution that represents these measurements, I would say theoretically, if you will. Okay? So you can collect these and create a histogram. You don't collect these, but there's this distribution that describes all of the measurements. Now, another thing important to point out is once we get into big boy, big girl statistics, where we start looking at the difference between, or not the difference, but the dynamic, the relationship between samples and populations, we get into different notation. In a sample, if I collect a mean, the notation I use for the mean in a sample is x bar. If I collect a mean out of a population, the notation is mu. So x bar versus mu. Which is the mean? Well, they're both the mean. This is the sample mean. This is the population mean. Same thing with the standard deviation. If I collect a standard deviation over here, I use an S or possibly an S. If I have a standard deviation from a population, I use sigma. So which one is a standard deviation? Well, they all three are. Sx is a standard deviation notation, S is a standard deviation notation, and sigma is a standard deviation notation. It depends on whether it comes from a sample in these two cases or whether it comes from a population in these two cases. Guys, it turns out that normal distributions are defined by their mean and their standard deviation. If I know the mean and I know the standard deviation and I know I have a normal distribution, as you're going to find out in future videos, I find out all sorts of cool stuff about that distribution. This notation is often given as a capital N with the number of the mean going first and the number of the standard deviation going second. Now, we also have up here, we have the variance. Over here, that could be the variance or that could be the variance. It should make sense to you that sigma squared will be the variance in a population. Okay? Now, let's investigate different things. Let's say that I have a normal distribution where I have a mean of 20 and a standard deviation of 5. What that tells me is on the number line, if I'm going from 0, 5, 10, 15, 20, 25, 30, 35, up to 40, I can think of this right here, and this tells me that I have a normal distribution with a mean of 20, and I have a standard deviation of 5. Guys, the mean is a measure of center. The standard deviation is a measure of spread. So I know that if I have a 20, that my distribution is centered at 20, and it's spread 5 units to the left and 5 units to the right. So I can draw this normal distribution like that. Now, compare that to a distribution, for example, that has a mean of 15 and a standard deviation of 3. This tells me that the distribution I'm looking at right here would be centered at 15, 3 units to the left, and 3 units to the right defines the spread. Now notice this distribution is taller and not as wide as this distribution. Why? Also notice this distribution right here is centered at 20. This distribution right here is centered at 15. So this first number tells me where the distribution is centered. This next number tells me the variation, the variability around the center. So a standard deviation of 3 versus 5 says I have less variability. And to make that variability smaller, we have to make the distribution actually taller. Okay? Now, let's take a distribution of what we call IQ scores. And it turns out that IQs are normally distributed with a mean of 100 and a standard deviation of 15. Now, what I know is I have a normal distribution, so I can draw the normal curve. Couple of characteristics about the normal curve. First of all, this line never touches the horizontal axis on either side. So this goes on forever and ever and ever and ever and ever, never touching. So it has asymptotic behavior on the left side and the right side. I know that smack dab in the center of the distribution is the mean, so I know there's a 100 there. And I know there's a point right here, and it's pretty easy to find. If you've ever had a calculus class and you've taken studied derivatives, you know that you've studied concavity. And if you haven't studied this, it's no big deal. Okay, but there's a point right there we call an inflection point where the concavity changes and has something to do with the second derivative. If you've taken calculus, you know what I'm talking about. I'm not going to get into it because I know most of you haven't. But anyway, there's a place right there. If you draw this thing correctly, this normal distribution correctly, you'll see that there's a place right through here where you almost have a straight line. If you come to the middle of that straight line and draw a point and drop that down to the horizontal axis, that is one standard deviation above the mean. Well, if I have 100 centered plus 15 units above the mean, that's the distance from here to here, then I know that this value has to be 115. Because of perfect symmetry, I know there has to be one standard deviation below the mean. So 100 minus 15 gives me 85. Now, once I establish that distance right there, I can go up here. That's going to be 2 standard deviations above the mean. I can go that much more. That's 3 standard deviations above the mean. And I can do the same thing down here. Now, I could go on and do, so I got the mean right here. So I could go 1 standard deviation above, 2 standard deviations above 3. I could go and do 4, 5, 6, 7. But typically when we draw a normal distribution, we stop at 3 standard deviations above the mean up to 3 standard deviations below the mean. Or okay, I said that backwards. We stop at 3 standard deviations below the mean up to 3 standard deviations above the mean. Now again, 4, 5, 6, 7, 8, 9, 10, 11 standard deviations above the mean and below the mean exist, but we typically don't include those in our drawing. Now, there's something called the empirical rule. The empirical rule is also known as the 68, 95, 99.7% rule, because it tells us that roughly 68% of our data falls between 1 standard deviation below the mean and 1 standard deviation above the mean. 95% falls roughly from 2 standard deviations below the mean up to 2 standard deviations above the mean. From 3 standard deviations below to 3 standard deviations above, we have approximately 99.7% of our distribution. And because we're describing 100% of our population, if we know that 99.7% goes from here to here, then we've got some that are missing. And because of symmetry, half has to go here and half has to go there. So from here up, starting at 145 up, or 3 standard deviations above the mean and up, I know that I have 0.15%. And from 55 down, I also have 1.15%. So I have this 0.3% divided by 2 that's missing from this 99.7% here. Now, guys, we got all sorts of information about IQs now. I know that you woke up this morning thinking, if I just knew more about IQs, my life would be complete. Okay, you probably didn't wake up thinking about IQs, but let's pretend you did. Well, you got a lot of information now. Knowing that we have a normal distribution, this empirical rule tells us that approximately, roughly, 68% of people has IQ between 85 and 115. Roughly, 95% of people has IQ between 70 and 130. Almost everyone, 99.7% of the people, has IQ from 55 to 145. Not many people, only 0.15%. Now, guys, in case your understanding of this decimal and percent is off a little bit, or a little sketchy, 0.15% as a decimal is 0.0015. So this is tenths, hundredths, thousandths, 10,000ths. So only about 15 out of every 10,000 people has IQ below 55. Only about 15 out of every 10,000 people has an IQ above 145. Now, we get people all the time get on Facebook and Twitter and take these goofy online IQ tests, and they score really, really high. And you know, they want to impress that they have an IQ of like 160, and maybe they do. It's doubtful that they do. Only 145 and above. Only 15 out of every 10,000 people has an IQ of 145 or higher. And that's fact. It turns out, and again, not one of these goofy IQ tests that you take on Facebook, but one that's given by a certified IQ test giver, which actually is my wife. She's a school psychologist, so she gives IQ tests quite a bit. But if you have an IQ of 130 or higher, and you have a documented test result, you can send that to an organization called Mensa, and they'll send you this nice little invitation to be part of their geeky little group, and you can become part of them if you so want to do, if you want to do so. So, and it's cool. Actually, Mensa has a lot of cool stuff going on. So it's I'm kind of poking fun at it, but it's a super cool organization. So guys, run out and pay I think $700, $800, $900 to get a certified IQ test, and if you get a score above 130, you can be part of Mensa. All right, ECTs form a normal distribution. Mean 20, standard deviation 5, let's say. So what do we know? We know that the distribution scores is perfectly bell-shaped and symmetric. We know that underlying this nice continuous curve is a histogram, but we don't draw the histogram. Once we get into big boy, big girl statistics, Let me get my previous graph here. Once we get into big boy, big girl statistics, we no longer look at the histogram that underlies the distribution for the population. We just look at the smoothed out distribution and erase all this stuff here. So this is all we look at. So we know smack dab in the center is the mean, which is 20. At this place right up here, again, think of that line going straight. Come to the center of it, drop a line down. That's one standard deviation above the mean. Come straight over, drop a line. That's one standard deviation below the mean. Once we establish that distance, we keep that distance consistent. And we can go 1, 2, 3 standard deviations below, 1, 2, 3 standard deviations above. We know that if this distribution, if this mean and standard deviation are true, that approximately 68% of people have ACT between 15 and 25. 95% has ACT between 10 and 30. Almost everyone has an ACT between 5 and 35. Only 0.15% has an ACT below 5. And 0.15% has ACT above 35. Okay? Now, put you to the test here. Let's say that we have a distribution. So there it is. Normal distribution, fill in the blanks. What's the mean? What's the standard deviation? Well, the mean's easy. Come to the center and drop a line down, so the mean is approximately 40. What's the standard deviation? Come to where it's, okay, so we're bending, stops bending, straight. Come to the center of that, drop down a line. What's the distance from here to here? Well, this is 40. This looks to be approximately, I don't know, what, 32? So the distance from 32 to 40 is 8, so the standard deviation will be roughly 8. Now, we get a lot better indication if this was drawn by technology, and this was drawn by me, which I did my best. So, what about this distribution? What would be the mean and standard deviation? Well, the mean, again, come to the center and drop a line down. So I'm going to go with about 54. Come to bending, not bending, straight. Come to the middle of it, drop down. So I'm about from 50 to 53, well, 50 to 54, say, something like that, yeah. So I would say that the standard deviation is roughly 4. All right, gang, that's all I'm going to do in this video. Next video is going to get pretty crazy. So take care.